we just computed the gradient of the minus the log likelihood function for logistic regression, and we're in the process of trying to get a maximum likelihood estimate for logistic regression. So the first thing that you might try if you were just tackling this would be to try to set that gradient equal to 0, and then that would give you a critical point of the likelihood function. But it turns out that unfortunately it doesn't seem possible to do that, and the reason is because this alpha is this vector of, where is it? This vector of quantities alpha I, and each of them is a nonlinear function here in the w's. And so even though it looks like we have this nice linear algebra expression for the gradient, if you were to try to set that equal to 0 and solve for w, you would run into a big mess because of that nonlinearity. But it turns out that we're going to compute the Hessian in a second, and it will turn out that the Hessian is actually positive semi-definite. So this L function is actually a convex function, and so we can use Newton's method, and Newton's method will give us a very nice way to actually algorithmically find a maximum likelihood estimate. So now let's do the gradient, or rather the Hessian. So we had the gradient here. Now let's take one more derivative of this. So we did wj. Now let's do also wk. So we differentiate this guy with respect to wk, and what are we going to get? Well, of course, the sum still sticks around, and we get, this is all constant with respect to w. These are just some data stuff. And we have to take the derivative of this. So we're going to get xij times the derivative of alpha I with respect to wk. So let's figure out what that is. What is the derivative of that? Well, we already figured out up here what the derivative of log of alpha was, and now we want to get the derivative of just alpha. So the derivative of log of alpha is, of course, the derivative of alpha over alpha. And so if we multiply over here by alpha, then we can get that the derivative of alpha equals alpha times the derivative log alpha. And that is alpha. This is for a generic alpha. I guess, so, yeah, I mean, this is for like alpha I, like one of the alphas. And then so it's alpha times this derivative, which is xj 1 minus alpha. So when we're differentiating, so that's when we're differentiating with respect to wj, when we're differentiating alpha I with respect to wk, which is what we're doing below, then we're going to get x, that'll be xk, so it'll be xik times alpha I 1 minus alpha I. Right, because it's going to be, this was for a generic x differentiating with respect to wj, and this is now, we have alpha I, and so it's alpha I is a function of x, the vector xi instead of just the vector x, and we're differentiating with respect to wk. So we get this, so let's grab that and use it down below. So that was the thing that we got. And so here, this derivative, this is the sum over I, 1 to n. This becomes xij, xik, alpha I, 1 minus alpha I. And now if you know your quadratic forms, you might, it might pop out to you that this looks like a quadratic form. So it's a quadratic form of some vector, let's say, let's call it zj, Zj transpose with some matrix. It's going to be, since it's only summing over from I from 1 to n, it's going to be a diagonal matrix. Let's call it maybe B with a vector zk. And here this zj is going to be, what's zj? Zj is going to be the x's, x1j up to xd, or not d, xnj. And similarly, zk will be, the same thing, but with k instead of j transposed. And this B matrix is a diagonal matrix. When you have an expression of this form, the matrix in the middle is a diagonal matrix. So this is, maybe I'll put it to be explicit, alpha I, well, not I, it's alpha 1. 1 minus alpha 1 down to alpha n. 1 minus alpha n. Sometimes we write diag of alpha I, 1 minus alpha I for this matrix. Okay, so that's nice. And now let's think about what are these z's here? This looks a lot like, I mean, are these actually, they're not quite the x's, because xi, or xj was x, that was the rows, right? It was x1j up to xd, no, x, wait, I'm getting confused. Right, it's x, sorry, xj1, it's the row, it's like the first row, the jth row. The jth row is xj1 up to xjd. And so these zj's are the columns. So this would be the jth column. Zj is the jth column of the design matrix. So we got this expression here for these second derivatives, and it was this nice thing, zj transpose bzk. And this is actually the jkth entry of the Hessian matrix. That's the definition of the Hessian matrix of this function. So the zk entry is just this. So since these z's are the columns of A, then we need to take A transpose to get the column, to make it a row, and then times B times A again, and then to multiply back down by a column. So the jkth entry of this will pick off the jth column, will be the jth row in A transpose, and then it multiplies times B, so looking at this thing, and then it multiplies, so the jkth entry would be the jth column of I times B, that's this, times the kth column of I. And so we just get back exactly this thing for the jkth entry. And so therefore, the Hessian matrix of L is exactly this. Let me put it in a different color to make it, to emphasize that. The Hessian matrix of L, which we write this way, this sort of gradient squared looking thing, is A transpose BA, where A is, of course, that design matrix thing, and B is this matrix here. It's diagonal matrix. All right. Very nice. So we got some very nice, very beautiful, simple linear algebra expressions for the gradient and the Hessian. But there are some nasty nonlinearities hanging out. Of course, these are 0 on the off diagonal. Some nasty linearities hanging out in each of these. But they're not difficult to compute. We can always compute them quickly, so that's good. And now let's think about, I claimed before that that Hessian was going to be positive semi-definite, so let's just see why that is. Well, the entries of the diagonal entries of this B are these alpha times 1 minus alpha quantities. And let's just, to remind ourselves what the alphas are these sigma of something, and that's 1 over 1 plus e to the something. So this is always a positive quantity, and so the sigma of something is always going to be a positive quantity, and it'll be non-zero. It's strictly positive. And so therefore something positive times something, and it's also, well, I guess also we needed it to be less than 1, so it's also it's let's see, so it's less than 1 because, well, for the same reason, because this is always positive, so it's always the denominator is greater than the numerator, so it's less than 1. Positive and less than 1 times positive and less than 1 is positive. So the square roots of each of these entries exist, and they're real valued in particular. So let's do that in a color. There we go, color. We can take the square root of this B matrix, then that's a real symmetric square root. And this thing then becomes square root of B A transpose times the square root of B A. And a matrix like this, you can check, you can verify that the eigenvalues are always non-negative. That's an easy thing to check. And so that implies that this Hessian is positive semi-definite, and therefore L is convex. So that's a very nice thing. It's not necessarily strictly convex, because the Hessian is not necessarily positive definite, but at least it's convex, and that's a great sign for, makes it a prime candidate for optimization methods. And so so we don't run out of time in this video, let's save that for the next video. We'll see, so we could leave it here. We've got the gradient, and we've got the Hessian, and it's positive semi-definite, so things are all just perfectly set up for Newton's method. And we could just say, okay, now apply Newton's method, and you can iterate and get the answer. But I'd like to show you actually what it looks like applying Newton's method here, because it turns out that the solution, the update equation for Newton's method, in this case, turns out to take the form of the solution to a weighted least squares problem. And so that the resulting method is sometimes called iteratively reweighted least squares. And that's something that's good. It's good to know what that means. So let's take a look in the next video. We'll take a look at what it looks like when you apply Newton's method to this setup and optimize to get the maximum likelihood estimate for logistic regression.